Algebra 2, Chapter 16.2, Solving Exponential Equations. In 16.1, we went over properties of logarithms, and this section, 16.2, is very much related to that. So the essential question, what are some ways you can solve an equation of the form a times b to the x power equals c, where a and z are non-zero real numbers and b is greater than 0 and not equal to 1. Solve exponential equations of the form where a, so anyway, that's the standard. So we're given some examples here. First, look at the equation 275e to the power of 0.0x equals 1,000. To solve this equation graphically, split it into two separate equations. And so we're going to have, first of all, the left side will be y1 equals 275 times e to the power of 0.006x equals $1,000. Now, you may not realize this, but this is an actual interest rate problem. So if you had $275, how long under continuous interest at a rate of 6% annually will it take to reach $1,000? And what will the graphs of y1 and y2 look like? Well, y2 is going to be, I'm just making a sketch, y2 is going to be just this, y equals 1,000. And y2 is going to be this thing right here. You got your starting value of your y-intercept is going to be 275. Our initial value, and then the curve is going to go up like this, and eventually there's going to be an intersection point, which will give you the amount of time that it took for this $275 to become worth $1,000. So that'll be our solution. So that's basically what it's going to look like. Now let's go here. It says graph y1 and y2 using a graphing calculator. So we'll go to our calculator here. We have a sketch in the material here. But if we go here to 275e, now I press second division sign. E is Euler's number, which is about 2.718, I think. A very special number named after Euler, German mathematician. So anyway, we're going to have our y2 is 1,000. And when we graph this, we do not see anything because our window is not right. So to get our window right, we're going to go from x minimum. We'll start at, I guess we can start at 0. And I don't know how long it's going to take, but I'm going to give it 20 for 20 years. And then y maximum, we know that we're going to have at least 1,000 at the top. So I'm going to put 1,500 here at the top. I'll go by 100. So I hope that we're going to see the intersection point in the graph here. Now we do not quite. Okay, so all we have to do is go to window and instead change x max to 30, as in 30 years. Now graph, we should see intersection. So that's it. And to find the intersection point, we go to second, trace 5, enter, enter, enter. So we get 21.5, x equals 21.51652, we'll call it. So 21.52, in the context, that's going to be like years if we use the. Okay, so that's how we would find that one. Now let's go ahead and look at, okay, let's go look at this next one. They give us another one. Look at the equation 10 to the power of 2x equals 10 to the power of 4. So 10 to the power of 2x equals 10 to the power of 4. So we can just put those in the calculator too. So 10 to the 2x. So 10 to the 4th, it's going to be a similar sort of thing. 10 to the 4th, is it going to be 10,000? So y equals 10 to the 4th. And then 10 to the 2x is going to go like this. Same thing, go to our calculator. So 10 to the power of 2x equals 10 to the power of 4. And I think 10 to the power of 4, that's going to be 10,000, isn't it? So we graph this, and we don't see a whole lot. First of all, we're not high enough because we need to have 10,000 up there. So we go to our window. I'm going to change my window back to my x max back to 5, and my y max has to be at least 10,000. So I'm going to make it 11,000. And we're going to go by thousands here. We should be good here. Yeah, so we get this, and we get an intersection point. Second, trace 5. Enter, enter, enter. So x equals 2. So the x coordinate is 2. So I'll put x equals 2. So the solution to the equation is x is approximately equal. It's exactly equal to 2. Okay, so there are other ways to solve this graphically with little situation there. Now, what we're going to look next at is solving equations algebraically. And they start us out giving us an equation and then go through the process. And in the process, what you do is use your properties of logarithms to solve. And if you look back at section 16.1, I think that was what we did there as part of the exercises. So we're going to they give us an example here. You can look at it and pause there. I'm just going to go on to actually work these out. So if we have this equation in example B, 5 to the power of x minus 4 equals 7, and this is our original equation. So what are we going to do to solve for x? Well, we're going to add 4 to both sides of the equation. So when we add 4 to both sides of the equation, negative 4 and positive 4 cancel each other out. So we have 5 to the x power equals 11. And now what we can do is take the log of both sides. So the log of 5 to the power of x is log of 5 to the x power is going to be equal to log of 11. So if we use the power property of logarithms, we take this x out front. So we can rewrite log of 5 to the power of x. And whenever we see log, just log, that means log base 10, which is helpful because that's one of our standard calculator keys. So what we're going to have is on the left side is x log 5. And so to solve, x is going to be equal to, dividing by log 5, x is going to be equal to log 11 divided by log of 5. And now we can just do this in our calculator. So you have here. So we put log 11 divided by log 5. So we get about 1.49 rounded to the nearest hundredth. So it's approximately x approximately equal to 1.49. So really that's it. So that's an algebraic solution right there. So let's go on to the next thing here. Okay, we give another equation here. We give reflect. Consider this equation. 2 to the power of x minus 5 equals 85. How can you solve this using logarithm base 2? Well, what we can do is we can write the left side. So 2 to the power of x minus 3 is equal to 85. So what we can do is we can take both sides, log base 2, let me write it down here, log base 2 of 2 to the power of x minus 3 equals log base 2 of 85. Well, on the left side, log base 2 of 2 equals 1. So all we're left with is x minus 3 equals log base 2 of 85. And then adding 3 to both sides of the equation, we have x is equal to log base 2 of 85 plus 3. And then we can use our change of base formula. Again, that's from 16.1. We can rewrite this and solve this as log of 85 over log of 2 plus 3. And so we can get to our calculator and see, we can go like this. Log of 85 over log of 2 plus 3. So get about 9.41. So that's how we would solve that one. Okay. Next you have a your turn example. I want you to see if you can just pause this video, see if you can work out this one on the left, and then I'll go ahead to see if you got it right. Okay, first thing here with this one, 2 times e to the power of x minus 1 plus 5 equals 80. First thing, subtract 5. So we have 2 e to the power of x minus 1 equals 80 minus 5, or 75. Next thing, we divide by 2. So we have e to the power of x minus 1 equals 75 divided by 2, which is 37.5. And then we can cancel out this e by taking what is log base e is the same as natural logarithm. So if we take the natural logarithm of both sides, the natural logarithm of e to the x minus 1 equals natural logarithm of 37.5. And ln and e will cancel each other. The log base e of e is 1. So we have x minus 1 equals natural logarithm of 37.5. And we add 1. We're going to have, just we're going to write here, x is equal to natural logarithm of 37.5 plus 1. So x is going to be approximately equal to, go to our calculator. Well, that's an exact answer right there. But to get a fully, put these terms together, I would just put them in the calculator like this. We go to natural logarithm of 37.5 plus 1. So about 6.42 or 6.424. Okay, and so really that's going to be it. Let me see, did I get that right? 4.624. Yeah, I just wrote it down wrong. There we go. Okay, now why don't you go ahead and see if you can work out number 5. Okay. Again, what we have is we have 6 to the power of 3x equals 12. So what we can do is we can take log base 6 of both sides here. So we can rewrite, so I'm going to put 6 to the 3x is equal to 12. So let's put log base 6 of 6 to the power of 3x. And that's going to be equal to log base 6 of 12. So log base 6 and 6 will cancel each other. So we have 3x is equal to log base 6 of 12. And if we divide by 3, we have x is equal to, I'll put 1/3, and we can use the change of base formula, log 12 over log 6. So let's go ahead and put this in our calculator. 1/3 and then we're going to have log 12, oops, let me put it out here, times log 12 over log 6. So we're going to get about 0.462. So really that's going to be it. There's another problem here that's involved compounding quarterly, but we're not going to do that here in this introductory video. I hope this has been helpful to you. Good luck.